Am I hello? Am I audible?
Yes, sir.
Am I audible? Hello?
Yes,
Yes,
sir.
sir.
Last class, we were discussing about how we can use 2148 generate different signals. We have written a square waveform on P0.3, and we've seen that. So to continue our discussion from there, so let me run once more. So we have generated with a particular delay. So I have to generate a rectangular waveform instead of a square form. So what do? I just change the delay value. So on time, I can make it more. Let's say I'll make it 20 milliseconds. Off time, I'll make it 10 milliseconds. I can able to generate. So you can just see that it is an asymmetric. So with a different duty. So now the on time is different. It's more. So like this, I can able to generate so different signals on the different pins of the microcontroller, and so that we can able to interface many number of devices. Now we will add one more interfacing element to the LPC2148 and see that how we can read the data from the microcontroller. Statement for me is so interface an LED and a switch, a push button switch to the microcontroller, and write a program to blink the LED when the switch is key pressed. Now 0.31, so it is connected in the common anode, and 0 the LED glows. Whenever I send 1, the LED is on anode mode. Now I'll be connecting a switch to the LPC2148. I can use any of the port pins. I have assumed P0.14. So now this is a push button switch. So whenever the switch is pressed, both the terminals, this switch produces the different voltages, and the P0.14 is when you have not pressed the switch, the voltage what you are getting is a 1 because it's internally pulled up, so that you get 1 here. Or explicitly you can connect a resistor here and connect to the 3.3 volts. So when you don't press the switch, it is always certain that you are applying the logic 1 at this pin. Whenever the switch is pressed, so the switch in to the ground. So what is the voltage you receive at this point is a 0. So that means that when the switch is not pressed, you are going to get 1. When the switch is pressed, you are going to get a 0 here. Now we will learn how to read the data at the GPIO pins in the microcontroller 2148. We know that there are 2 registers are available which are meant for setting the pin 0 or 1. Now I am not sending the data output, I am reading the data. So first I will define the problem statement. So and switch to P0.14. Okay, so this is the interfacing. I have done it. Interface an LED to P0.10 and switch to P0.14. So I have connected a switch to the P0.14 now. Now I want to read the status of the switch and set it to whatever the switch value is there. I have to just set to a particular pin. So to make it simple, so I will just remove this for a moment. So I'll put it outside. I'll make it comment. Okay. Now, so look at this program for a moment. Now, what is my job? I want to read the switch. So as soon as I read the switch, I'll make the LED connect to P0.3 on and off whenever the switch is pressed. I want to do the job. So what is the way we can able to read a switch? Now, there is a register is available inside the GPIO block of 2148. The name of the register is called 0 pin. So for the IO 1 pin, I can able to use it. So I am using it. So now, whenever I read this register anywhere in the program, so the moment you read this register, it is nothing but reading a 32-bit integer. So you're going to get a 32-bit number from this register. Now, this register gives the status of the data present at all the 32 pins of the port 0. For example, if IO0 pin is a 32-bit register, the lowest bit, that is 0 bit, gives me the data present at P0.0. the last bit of IO0 pin, that is 31, bit 31, gives me the data of this. I can able to collect the data present at the different pins now. So this is the only way I can read the data from the microcontroller. There is no other way possible. So now, if I want to read this data and extract only information related to a particular pin, now in this case, P0.14 is the pin I am interested. I am not interested in other pin. So, but there is no way you can read only one pin, because I can read only the complete register. So I can get 32-bit number, but in that I'm interested in only one bit. So what do I do it? So one of the method for that is, so you read, and then we have all the bits 0, just read that bit. So we have learned that in assembly there are instructions, bit manipulation, we do it. So takes the data of a required bit, all other bits becomes 0. So then what is an operation I supposed to do it? So whenever we want to do that type of operation, we know that bit and we have to use it. Now, which is a bit I'm interested? I'm interested in the 14th bit. You have to prepare a pattern. So that means that you are making all the bits 0, 0, 0, 0. 14 bit you are making it 1, and the remaining bits you are 0, 0. So this is one method of, you have to write the pattern and then convert it to hex and then use in the AND operation. Other method is there. This is a shortcut method in the C, we can use it. So to generate a 32-bit bit pattern where the required bit can be 1. How? So you want the 1. So what I'll do is I'll take 1, that is since it's 1 is a constant, I'll say unsigned. One new means it's nothing but 1, so it's an unsigned constant. So then I left shift this by 14. So look at this, the operation. Whenever I do like this, that means that 32-bit number or bit pattern is generated. In that, all the bits become 0 except the bit 14 becomes 1, because I am shifting the 1 14 times. So now once this mask is ready, I'll add that mask. So with the register which I am reading from the Lpc2148. So now, so the moment I perform an AND operation with this bit pattern, so the overall value of this, either it becomes 0 or 1, depends upon what is the data present at the pin 14. Because why? You are ANDing it, you are compulsorily making all the bits 0, only retaining the 14th bit. So the 14th bit dictates the value of this operand. So if the 14th bit is 1, the overall value becomes what? It is a logic 1, in the sense it's a positive number. If the 14 bit is 0, the overall value of this operand becomes what? Becomes 0. That is logic 0. So this concept I'll be using it to read the switch. So now what I'll do is, so I know that, so this value, whatever the value I have now, so I can use with an if operation. So I can just combine that. So if the total value, whatever I have now, value, if it is equal to 0 or not equal to 0, these are conditions I can use it now. So now look at this. So this total value, I can remove this also, one bracket, or I can have it, no problem. Okay. So now look at this. If this is 0, what is the meaning I get? The meaning I get is, that means that this key is pressed. So whenever the value key is pressed, the voltage at this point becomes 0. That means that if the if condition is satisfied, So that is, this condition is satisfied. That means the key is pressed. Now, so once this identification is done, then I can do whatever I require. For example, I want a simple logic. I want to set the LED on whenever the key is pressed. When the key is not pressed, I want to switch off the LED. Let's say that's the concept I want to do it. How do you make the LED on? By making P0.31 properly. So I will just type P0.31. That is nothing but IO 0 set. So IO 0 set. So which is a pin. So I'll be using now this shift concept. So 1 U left shift 31. So whenever I just write like this, what will happen? 32-bit pattern in the last bit will becomes 1. So that will be written into IO set. So that means pin is. So now you have to just see that diagram in this case. So I have to send to make LED. So I have to make it what? 0, because it's a common anode. So I'll make it 0 instead of 1. So instead of set register, I'll use a clear register because I have to make it 0 on. Else, if the key is not pressed, so else if the key is not pressed, so LED. So let's say IO 0 set 1 U left shift 30. This logic. So this logic contains both reading and writing to the microcontroller using GPIO pin. So I am reading pin 14, checking whether the bit is become 0, that is pin becomes 0, that means the key is pressed. Then I am making P0.31 0. So else I am making the bit P0.31 is equal to 1. So this I'll repeatedly execute. So now I'll compile this program. So I'm not using a program. So let's say I'll run this program. So now it is high is there. The value is high in the sense P0.31 I'm plotting. Whenever it's high, what does it mean? That LED is not glowing. So now what I'll do is I'll go to the pin numbers. See that I'll pinch. So you can, through the mouse, you can make any of the pins 0 or 1 in the simulator. So whenever you make 0 or 1 explicitly through the pins using your mouse, it is equivalent to pressing the switch only. So now I'll go to the P0.14. See that this is 0 and this is a 14. So now I'll press the switch. When I press the switch, it becomes 0. When a tick is there, it is 1. So I'll make it. See that the values. You can look at the oscilloscope. See that oscilloscope is changing. The value is changing. Each time I click the switch, so it is becoming what? LED becoming on and off. So I'm just changing it. So as soon as I apply the input, the program runs that and appropriately changes the value at the P0.31. So this is how we can read the data at the any pins of the LPC 2148, either port 0 or port 1. Only thing, appropriate register, you have to use it. Now, like just we'll make a simple change to this program. So whenever the switch is pressed, I want to generate a waveform. Whenever I hold the key. So what I'll do is I'll remove this logic now for a moment. So this is one logic. So now I'll remove this logic. I want to put a waveform to be generated whenever the key is pressed. So now within the if condition, I'll put the logic for generation of a waveform. So this is the logic for generation of a waveform. I just bring it. So what is the logic I've done? So when the key is pressed, the waveform has to be generated. Whenever I release the key, the waveform should stop generating. So I've just connected the waveform program to the switch. So let's compile this program. Even the direction also. So instead of liking like this, we can write the left shift pattern. That means that, so 1U left shift 31, I can write it so that it is equivalent to writing like this. You can always use this method wherever required. So now I'll compile this program. Okay. So now I'll run the program. Now there is no waveform is there because I have not pressed the key. Now go to the P0.14 pin, press the key. Press the key means what? Just make it 0. See the waveform comes. Now waveform is continually coming because I'm holding the key, pressing the key. If I stop the key press, the waveform stops. So like this, you can able to control the output activity by the input activity. So this is one of the functions of an important equipment or an experiment called logic controller. So logic controller means what? Many outputs will be there, many inputs are there. So based on the inputs, you are applying certain algorithm or logic and generate different outputs. So this is basis for designing an equipment called PLC, Programmable Logic Controller, or PLC module, which is extensively used in the industry to control the different machineries for different operations of the machineries. So they're called as CNC, computer numerical control machines. These machines, every such machine will require logic controller called PLC. So now we have understood this one. Now we will go to another program. Now, so we will take one more now. So let's design a traffic signal, which you already know that we have done in Arduino. So we will do with Lpc2148. Now the question is interface 3 LEDs to Lpc2148 and write an embedded C program to simulate a traffic light system. So what we do, we can assume, I have assumed P0.0, P0.1, P0.2 to be used to connect 3 LEDs. At one junction I have taken it. I have connected in common anode. So that is all the, this is, to put it the other way, the anode should come this side, the cathode should come here, because you're connecting always the 3.3 volts to the anodes. So it is just reverse this LEDs. So now, whenever I send 0, the LED glows. So whenever I'll make it 1, LED is off if it's a common anode. Or if you want to use a common cathode, that is you don't want to change the LED connection, instead of making 3.3 volts, I have to connect to ground. So that is the one you have to make an assumption there. Now, so I have written a small program here. So you can just look at this program. I defined the 3 different values for the how much time the green signal has to be on 30,000 times the value. So how much time the yellow signal should appear. So how much time the red signal like that it appears. So now, so first I have to set the direction of these 3 pins. What are the pins? P0.0, P0.1 and P0.2 as an output pins. So we know that IO direction register is used and the corresponding bits you have to make it 1 to make it output. So instead of writing this, you can also write, so as I said, so I will remove this. So instead of this method, you can always write like this. So for example, I want P0.0, so 1 and the 2. So that means that, so 1, U left shift the 0, that is P0.0 is required. So logical OR, because you require one more bit to be on, 1 U. So left shift 1, logical OR. So 1 U left shift 2, that is P0.0, P0.1, P0.2. All this you can connect them, these bits, that is these are the bits you want to make it on, and OR with the IO direction. Always better to use OR, because if at all if you have used IO direction in the program before this IO this statement, if you have some other statements where you used to set the IO direction bits, So if you say logical OR, you are not going to disturb those values. If this is the first statement, you don't require to logical OR it. So now just semicolon it. Now this is a one way of writing the program. So this is another way, making the bits 1 1 1, prepare a hexadecimal pattern, and you can write it directly to here. Now one job is ready. Now what should I do? Set the green for 30 seconds. So I'm assuming the first LED, the P0.0 is a green. So that means that I'm making that particular bit. So on P0.01. So that means that I'm using common cathode. So instead of 3.3 volts, you connect this to ground. So whenever you say 1, the LED will be on. So now delay of value 1. So value 1, I'm assuming this is for the green. So in that particular direction. So 1 is ready. After making it on for some time, so I'll just switch off the same green, and then I'll switch on the yellow or orange light. So that is the P0.1 again for 5 seconds. Again, I just switch on so the red LED. So for the value 3, that is around 50,000 so milliseconds. So that is a value I've used it. Now, so we can just copy this value. I can just run it one. So now look at this program. So delay value 1. So I will define the values. So these are the 3 defined values I've used it. So I use IO set 0. So instead of IO set 0, you can say IO 0 set. So this is O capital. Okay. So this is O capital I used. Okay. This is O. This is O. You should be very careful. O is different from the 0. So when you say IO, you have to use O. So properly I have to use. So delay MS is there. So I'll just change to delay. Okay. So here also in the prototype also I'll change to delay. So now see the program is ready. So what is this program? I'm doing it. So I'm doing this program. So to switch on the green LED for 30 seconds, yellow for 5 seconds, red for 50 seconds. So red for 105 seconds. So why we given more time means because I should allow other 3 signals, other 3 sites should be complete its operation. So for example, there are 4 sites are there. This is for program for 1 site. So whenever you're displaying red, that means that you are allowing other 3 sites should complete and come back to this site. So that is why 3 into 35, 105. I given this achievement. It's a part of junction with the 4 roads. Now, in every case, what I'm doing, I'm setting and clearing it. I'm just making that on and making it off. So let's run this program and see that. So in the simulator, we can see the changes in the particular bits. Now these are the bits which I'm going to observe it, P0.0, 1 and 2. So I'll run the program. So you can just see that the values. So I can just show you it's a so using the single step. So this is a first statement. So I'm just setting it all the bits 1 1. The direction register, these bits should be 1 1. So I'll execute the statement. You can see that all these bits becomes 1 1. So output becomes 0 0. So now I'll start the logic here. So I will just set the first bit. So first bit, that is green LED is on. So now the delay is there. I'll just skip that, step over that. Okay. So it has gone into that actually. Okay. So then I'll stop it. Now, for checking in the simulator, I'll just comment these lines to show it in a simulator. So its first LED is set. So there it is called. So it's called here. Okay. It will not compile.
Sir, the comment you
Yeah,
have
yeah.
given.
Yes, this is now the comment. Yeah. So I'll run this. So set the first one, it is on. So then switch off. So then I'm just second P0.1. You can keep observing here. Okay, then second one is the yellow is off. Then red is on. The red is on. So again red is off, and then it repeats. So if you just see that all the three, it is changing. If I run it fast also, so it is changing. So 1, 2, 3, it is going there. It's fast. Okay. So this is how you can able to build a traffic signaling system using LPC2148, using the none of the existing functions. See that in Arduino you use digital read, digital write like functions. No, it's not like that. Here you return every code without any library. That is from the lowest level and the lowest porting of the application. You are able to implement it. Now we'll go to the third problem. So now, so instead of this experiment, I will just go to one more experiment. Okay. Okay. So we will learn how to interface the stepper motor to the microcontroller. So we will understand the stepper motor concept, and then we will see that how I can interface a stepper motor to the microcontroller. So a stepper motor is a stepping device or a digitally controllable mechanical device or a motor. So normal motors, what you will see, like for example, the DC motor, what you see in the mixie or the fans and everything, if you switch on, it will just run at a particular speed for which it is being designed. So when you switch off, it will just stop after rotating for some time. Now I'm just giving a motor which is digitally controlled. Digitally controlled in the sense what, when I say digital, it is nothing but ones and zeros. So by generating ones and zeros through the microcontroller, I can able to make this motor rotate in steps. Whenever we have a digital control motor, the advantage is that I can control every step of its rotation. Let's say one rotation is 360-degree. If this motor is being designed inside to make 200 steps to complete one rotation, so that means that every one step I can control by generating the digital signals. So by generating ones and zeros, I can make it rotate 5 steps, 10 steps, and stop it like that. So I can able to control the precise moment in terms of degrees of this motor. Since I'm able to control the precise moment of this rotation and stop it whenever I require it, I can able to convert this rotary motion into linear motion also by using proper mechanical the introduction here. That is a gears and other things we can introduce. So or some mechanism which can be attached to this shaft of this motor to convert rotary into linear motion. So whenever we are able to control this rotation to that accuracy in terms of steps, let's say 200 steps constitute one rotation, means every step I can control. Only if I give a signal, it runs one step. So that linearly also I can able to control that motion of a particular linear mechanism. Maybe you connect it to a mechanism in a CNC machine, that is which is controlling the x-axis movement of in a CNC machine. So I can say that move 10 mm, move 15 mm, so that the explicit the movement of the mechanical piece I can control through the digital information which I can generate from the microcontroller. Now we'll see that whenever we purchase this type of motors from the market, what are the things I should take into consideration and how do I write a program to control this one. This digitally controlled stepper motors have the advantage of having accuracy in terms of rotation, in terms of linear motion, and also I have the facility through program I can control the direction of the motor also. I can make the motor rotate clockwise or through the anti-clockwise by able to change the pattern of generating the waveforms, whatever I can generate here. Now, these stepper motor inside, basically it contains a mechanism like this. It contains a rotor and a stator, two parts are there. So one which is stationary is called as a stator, the other is the rotor. So these are forms, other thing outside is called stator, this is called a rotor. The rotor can be permanent magnet type, so it's like a magnet type. So there are the stator is controlled by basically the 4 windings. So by making these windings on and off, I can able to create a magnetic field so that the rotor can align to particular direction. So if I energize this winding to north south, so then energize this winding, what will happen? This magnet rotor align to this position. Then I switch off this energization. If I switch on this energization, that is the next one, the rotor aligns to the next position. By changing the switching on and off of the windings in a particular order, I can make the rotor align to the different position or make the rotor move in the clockwise direction. So if I energize these windings, see one, then next this is one, this is one, this is one, that is in the clockwise, the rotor moves in the clockwise direction. If I energize these windings, stator windings, in the anti-clockwise, first I'll make this one, then this one, then this one, then what will happen? The rotor rotates in the anti-clockwise direction. So effectively, the motors what is available in the market will have the 6 wires will be there. In that 4 corresponding to the windings. So the 2, the common of them, the 2 windings which are connected together and connect to the power supply. So any motor requires a power supply. So if you purchase the market, there are 6 wires will be there. Sometimes 5 wires will be there. If the 5 are there, 1 is for the power supply. They are already internally connected. If there are 6 is there, so you have to identify the common these 2 wires and connect to the plus 12 volts. Now, after connecting them to the plus 12 volts, Now I am left with what? The 4 windings, which I have to drive them in a clockwise or a anti-clockwise. Let's say these are the 4 windings in order I given A, B, C, D. Now I have to drive these windings. So what is the pattern I have to drive? I said if I drive in a clockwise like this, first this one, then next the B, next the C, next the D. So then motor rotates in the clockwise. So if I energize them in anti-clockwise, that means that see that first D, then C, then B, then A, motor rotates in the anti-clockwise. So now we have understood what is the program which is required to be generated for these windings. Now the question is, now I have understood the logic required. So now 4 pins of LPC2148 are required to generate these sequence of waveforms at these windings A, B, C, D. So I've chosen 16, 17, 18, 19 of the microcontroller to control these 4 windings. Now the question is, can I connect directly P0.16 to the winding A? That is, the moment you purchase the stepper motor from the market and purchase an adapter for 12 volts, because the stepper motor is a 12 volt stepper motor, you connect the 12 volts, the voltage wire, and other 4 wires. Can I connect directly to the microcontroller 16, 17, 18, 19 directly? It is not possible. That is where the concept of interfacing is required. The understanding of interfacing is required. Because why? The requirement of these wires, 4 wires, are different. Because they require what? The 12 volts power supply, and the more the current is required to make the stepper motor run. If you're taking a bigger stepper motor, what may be the difference? The current requirement of these 4 windings may be different. Voltage may be same, or the voltage also may be 24 voltage, and the current can also be the more. But whereas the microcontroller can generate at these pins only logic 1, that is 3.3 volts or 0. So it can generate only 3.3 volts or 0 at every pin. So that means that no way these pins of the microcontroller can sufficiently supply the voltage and the current required for the device. So in such cases, what we have to do, we have to introduce interfacing elements. So what are the interfacing elements I'm introducing here? So here I'm introducing an interfacing element called a transistor. So transistor is also called as an amplifier. One of the application of transistor is what? Is an amplifier. How do you use a transistor as an amplifier? So I've taken one transistor, like say SL100 or something similar such transistors you can take it, which has the capability to supply the current required for the stepper motor. This is the one you have to choose it. For example, if it draws around 0.1 ampere for every winding, so this transistor should be capable of allowing the current 0.1 ampere to flow through this transistor. So I've just taken the suitable transistor. Now the collector of the transistor I've connected to the winding. The emitter I grounded it, and the base of the transistor I connected to P0.16. Now whenever P0.16 I'll make it 1, that is a logical 1, through the program using a set instruction, then what will happen? The base conducts. Whenever the transistor conducts, what will happen? It is like a switch. It is like a short. It gets shorted. Then what will happen? Then current flows through this winding. So see, from the 12 volts, the current flows transistor. So your low winding is excited. That means that magnetic field is suitably created. So the rotor aligns to the new position, new step. So rotor moves to the new step. So this is how transistors are used to provide necessary interface between the stepper motor and the microcontroller. This is one method. So once I design this circuit, now I have to run this program. So what I'll do is, so I go to here. So now I'll just copy the program which is for the stepper motor. Now look at this program for a moment. Now, what is the program I have done this? I have done here. So delay ms is there. So I'll just change it to delay. Okay. So now look at what are the steps required. I have used 4 pins, P0.16, 17, 18, 19. So in the circuit diagram, you have seen that 16, 17. Since I'm using them as an output pins, because I'm generating the waveforms, you have to using as an output. So what is the first requirement? Set the direction of these pins as an output. So now, so which is a register? IO direction register. Say this digit, so represent what? 0.16, 17, 18, 19, this digit. So I'm making this digit 111 so that you get a F. So now I write this value into the IO direction register. Now the direction is set. Now I will make the motor rotate both in the clockwise and anti-clockwise. So I will just declare 2 variables. So which says that clockwise 100 times you rotate, anti-clockwise rotate 100 times. So now, so after that is done, so now look at the first thing. What is I supposed to do it? To make the rotate in a clockwise. Now each time, so I want to excite one winding, energize one winding. What should I do? First I have to switch off all the other windings and energize only one winding. So what I do in the beginning of a program, every time I'll just make all these 4 points 00 first by using IO clear register and apply 00 to these points. After applying 00, then I will apply 1 to one of the windings, so that what will happen, only one winding gets energized. The next what I'll do it, again I'll apply 00, I apply 1 to the next winding. So this sequence I have followed in the program. You can just see that I first make 0.16, 17, 18, 19, 00. That means that all the windings are de-energized. Then I'll set winding A energized, that is 0.16, that is I made it on. Then it is very essential, since it's an electromechanical device, it will not run at the clock speed of the microcontrollers. Microcontrollers run at 60 megahertz, whereas the mechanical devices run at very slow speed. So you should give certain delay before energizing the other winding and making the rotor to move to the next step. So if you don't give a delay, you can see the vibration in the stepper motor and the motor is not rotated properly. And also by introducing a proper delay, you can control the speed of rotation also. This is one of the advantage. So now I'm calling for a delay second. Okay. Now each time, so the moment you execute this statement, now one step is rotated. Because why? Because you energize the coil, the rotor moves to the next alignment position. So now what I'll do, I just executed a statement saying that decrement the number of steps clockwise by 1. See, minus, I given a pre-decrement operator. Then I check whether it reaches 0. If it reaches 0, this variable, I'll break from this loop. Otherwise, I'll continue. Now, same thing I've repeated for the other three windings. Only thing, what is the change? You can see that second winding I'm energizing here. So third winding C and the D winding I'm energizing. Then after that, what will happen? I'll keep repeating it until all the steps are completed. So whenever you finish the first 4 windings energization, you have to start repeating the same again in the same order, because how many windings you have? Only 4. So you should keep repeating in order. First 1, 2, 3, 4. Again what? So you should continue. After finish this energization sequence, you have to go back to what? Again from the beginning. So then what will happen? So rotor keeps moving in the clockwisation step by step. So each change of winding sequence will make the motor move to one step. So now, so I have done this one. So to move the stepper motor to move clockwise, so how many steps? Number of, let's say 100 steps. So if the 200 steps is 1 revolution, so then what will happen? 100 steps, so we'll produce 180 degree. Then I've done another program. So this is for anti-clockwise. Only thing is what? Everything in the program is same thing. Instead of energizing A, B, C, D windings, I'll energize the D first, then C, then B, then the A. So I'll repeat this. How many times? Number of steps anti-clockwise. So now 180 degree clockwise you rotated, 180 degree anti-clockwise you rotated. Now the whole program I put in the do while loop again. So you can just see that I am just putting this in a while one, so that what will happen? This program will continuously keep running it clockwise and anti-clockwise the motor continuously. So if, for example, for a particular job, you are interested only to rotate particular and stop it, you can just stop the program there only. So now we will run this program. So, and we will see that how the waveforms can be generated at the different one. So before we move to that, there is one formula is there in the stepper motor. So the formula is, so we can always, so this is the formula. What is the step angle? Step angle is nothing but the total number of degrees for one rotation, that is 360 degree, divided by total number of steps which constitute one revolution, that is 1.8 degree. So this is called a step angle of a stepper motor. So this is based on what number of steps are there for one version. This is given for every stepper motor. Generally, what is available in the market. So for a normal stepper motor which is used in the projects, it's a 200 steps. It's called a 200 teeth shaft. Even though we say 4 windings, so there are internally many teeths are there. Each winding is realized using many number of teeth. That's why 200 teeth shaft is there inside. So that is why you can able to realize 200 steps. So sometimes what we do is, so instead of using the transistors, we can also use a ready-made ICs are available. So it's called driver ICs. So one of the popular driver ICs is called ULN2803. This is one of the very popularly used to drive the stepper motor and also DC motor, other types of devices. So this IC has got internally 8 transistors are there. So in that I am using the 4 transistors. So look at that. The pin in 1, in 2, in 3, in 4, they are the inputs to the transistor drivers, and the outputs 1, 2, 3, 4, they are connected to the windings. So we have used a small resistance, but if any damage happens, correct now. So this there is no burning of the transistor, the driver IC happens, and no damage to the controller and other circuits. That's why we just generally use 47 ohm resistor. By chance if it gets shorted, nothing will happen to this IC. And the 2 points are provided for this IC. One is to be grounded 9 at the pin number, which is common. We should be connected to the 12 volts. So instead of this discrete transistors, you can always go for, this is called driver IC. Example is ULN2803. So the common should be connected to the 12 volts. So the other ground should be connected to the normal ground of your microcontroller board. So then you can use 4 of them transistors what is present inside among the 8 to drive the windings. So either you can build this type of circuit, or you can build this type of circuit whenever you purchase the motor from the outside market. Now, so we will go here and run this program. So now I'll run this program. Okay, so in the here you can see the changes in 16, 17, 18, 19. So if at all if you want to show in the here also, then what you do, you have to go to the setup. So you can remove all. So you can remove all. You can insert the 4 windings which you want to observe it. So port 0.16. So then you can add one more. So port 0.17. You can add one more. So port 0.18. So I'll add one more. So port 0.19. So 16, 17, 18, 19. These are the pins I'm controlling. For each of the bits, since it's a digital bits, you can make it bit, and whatever the color you want, you can just set it. So similarly, this one you can convert into a bit. So this also you can convert into a bit. Okay. Now I converted all these a bit. So then I'll close them. So then I'll run the program in a single shot. You can see that the 4 waveforms generating at this point. You can also see that the 16, 17, 18, 19, the waveforms are generated. So the motor is rotating in the clockwise direction. So you can see that. You can zoom in. You can just see that the sequence of the waveforms are different. See that? So the first, this is on, second winding B, the third winding C, then the 4th winding, that is a D winding. So on. So windings are, so they are switch on in a sequence in a clockwise direction. That is why the motor is rotating in the clockwise direction. So similarly, you can able to write a program to clockwise also, anti-clockwise also. It is doing both actually. So I'm running for 100 steps clockwise and then anti-clockwise. So it's happening. It's so fast. It's rotating. So both are happening. You can comment one section. You can just observe it. You can again uncomment and comment the other section like you try. It's happening. So this completes. So today's discussion about how LPC2148 can be used to build different projects. So we build three different projects. So simple logic controller we built. Then we built a traffic signaling system. Then we built how a digitally controlled motor or CNC machines can be interfaced using the microcontroller or the computers. So who is sharing? You can just stop the sharing. Stop the recording.